right, gang, STAT1800. We're really kind of moving into big boy, big girl stuff in this one. We're going to look at what's called measures of variation for simple linear regression. Now, again, guys, keep your eye on the prize here. Well, I guess the eye on the prize is getting this class behind you, but again, we're looking at simple linear regression, which indicates that we have a single predictor. So we have a single x value that we're trying to use to predict a y value. And again, both are quantitative. So again, everything we're doing here is setting the stage for multiple regression, which has multiple predictors to predict a single quantitative dependent variable or single y. So guys, this is important stuff. We're going to establish a lot of terminology here. So measures of variation, we think about, we partition what's called the total sum of squares. And everything that we do in this part comes down to the relationship between these partitions of sum of squares. Now, I've taught this stuff a lot to undergraduate and graduate students, and I've found that the best way to visualize the sum of squares for the total expressed as a sum between the sum of squares for regression and sum of squares for error. Well, first of all, let me say that your book will have it as sum of squares total equal to the sum of squares regression plus the sum of squares for the error. But I think in looking at this, the best way to visualize this is using a graph. Now, you got to use some imagination here with me. Let's assume that, there's a bunch of data points that have been collected. All right, so a bunch of measurements, and we've created a scatter plot, and we have fit the model to it. But let's focus on just one point. So we fit this model to it. So this is just one point from the data set that's been collected. We got other ones here that have been used to create this model. But we're just focusing on that one because it gives us a better illustration of what's meant by these particular sum of squares, these different components of the sum of squares partitioning. So I've got my model, y hat equal b0 plus b1x, and I've got this point which has a particular x value, and it has a particular y value. Think just a generic ordered pair, 1, 2. It says we go over 1 and up 2. Well, it's got an x value, which in this illustration is 1. It's got a y value, which in this illustration is 2. So we're just calling it x, comma, y. Now, we've got these y values over here that range from, whatever they range to, the high to the low. We could come back to the center because we assume normality, and we could, without question, know that we have a mean y value. Well, guys, this illustration perfectly illustrates the sum squares total, sum squares regression, sum of squares error. So just focusing on this one x, what do we have? Well, right here, we have a value for the mean. Right here, we have a value for the predicted y. And right here, we have a value for the observed y. Well, guys, it turns out that this distance right here is the total sum of squares. So guys, the total sum of squares can be found by taking the y value minus the mean. But we want to do that for all of our points, and we have to square those. So guys, that's the formula, if you will, for the sum of squares total. Now, this total sum of squares can be partitioned into two parts. It can be partitioned into this part right here, which is the sum of squares for the error. That's the difference in between what we observed and what we predict. And the distance from right here can be partitioned into what we call the sum of squares for the regression, or the sum of squares for the model. So guys, we can see that the sum of squares for the regression can be what? It's y hat minus y bar, quantity squared, sum that up for all of our data points. The sum of squares for the error can be found by taking y minus y hat and summing that up for all of our data points. Now, what do we need in examining these sum of squares, this partition of sum of squares? We need the y value, we need the predicted y, and we need the mean. So guys, let's go back over to, I could do it with that, but I think I'm going to choose to go back to Stat Crunch. So guys, I want to get rid of the residual column, because I don't want that to get in the way. So what do I need to do? First of all, I need to calculate the mean for y, and we know that that's 9 across the board. For all of the x's, the mean for y is equal to 9. The next thing I want to do is I want to do my predicted y's, and I also need my observed y's. I got my observed y's 2, 10, and 15. So I'm even going to change that to observed y. So now I need to come in and get the predicted y. Well, guys, I can do that easily by going to regression, simple linear regression, taking x to predict the observed y, and I want to save the predicted values. So it created a new group right here. So guys, I want to get rid of that variable 4 because I don't like it there. Doesn't hurt anything, I just don't want it there. Now, what do I need to do? First of all, I need to come in for the sum of squares total. I need to take the y minus the y mean and square it. So I need to take the observed minus the mean. So guys, I know that I can come into data, compute, expression, and I can go build. So I can take the y value, minus the mean, and square that. And I'm going to call this sum of squares total. Now, I can, if I need to, go into column, summary stats column, and I can go sum of squares, and I can just come down here and go sum. Or I could just really just add it up in my head. So the sum of squares total is going to be equal to 86. Now, which one do we want to do next? Sum of squares regression or sum of squares model? Some call it model, some call it sum of squares regression. Or do we want to do the error? Well, guys, let's just do the error, the sum of squares error. The sum of squares error takes the y value minus the predicted value squared. So let's create that. So compute, expression. I really kind of want that, don't I? Well, no, let's just build it. So I want my observed y minus my predicted y. And I want to square that. And I want to call this sum of squares error. All right, gang, I want to add these up. And I get 8.643. Now, gang, if I'm telling you the truth, what does the sum of squares for the regression have to be? Well, this plus this has to be equal to 86, so 86 minus 8.643. So, gang, the sum of squares for the model has to be 77.357. Well, let's check it out. So let's go to Data, Compute, Expression, Build. And what we need for the sum of squares regression is we need the predicted y minus the mean. Quantity squared. And I'm going to call this, for obvious reason, sum squares regression. Uh-oh, what do we do? Okay, I see. First mistake ever, boys and girls. So predicted. All right, that should work. All right, so we have a new column here. And when I add this column up, summary stats, columns, so I want sum squares for regression, and I want to sum that up. Guys, everything that we're doing, we should get 77.357, which is exactly what we get. All right, now let's think about what we've got here. We've got some sum of squares. And what that's going to allow us to do, it's going to allow us to create an ANOVA table for regression. Remember an ANOVA table for ANOVA? Well, guys, it turns out it's practically the same thing. So what we'll do is we'll start out with our sum of squares. And we'll have our model term. We'll have our error term, and we'll have our total sum of squares. Actually, guys, that should be right here. So our model sum of squares was 77.357. Our error is 8.643. And our total was 86. The next thing we get into are degrees of freedom. Well, guys, our degrees of freedom for the total is just n minus 1. So, guys, in this case, we only had 3 values. So we have degrees of freedom for the total is equal to 2. Now, our degrees of freedom for our model are the number of predictors, including the intercept. So let's let K number of predictors including the intercept. Well, we've only got one predictor, right? X plus our intercept is 2, so we have 2 total predictors. So we have degrees of freedom 1. Our degrees of freedom for the error is going to be n minus k. So guys, n here is 3. We have 2 predictors. So the degrees of freedom for the error term are equal to 1. The degrees of freedom for the model plus the degrees of freedom for the error will always have to be equal to the degrees of freedom for the total. Guys, the next thing we get into is the mean square. Just like with the ANOVA model, the mean square is the sum of squares divided by its degrees of freedom. 77.357 divided by 1. 8.643 divided by 1. The next thing we do is we create our F statistic. Our F statistic is the mean square for the model divided by the mean square for the error. So we have 77.357 divided by 8.643. So we have 8.95 is our F statistic. Now, our p-value is found. We are dealing with an F distribution, degrees of freedom 1, 1. Only the degrees of freedom for the model and the error define your distribution. So we have this F distribution, degrees of freedom 1, 1. We have a test statistic of 8.95. Our p-value is the area to the right of that. So guys, we know how to do that. Calculator, F statistic, 1, 1, area above, 8.95. Our p-value is 0.205. All right, so guys, that is our ANOVA table. Now, wouldn't that be a pain in the tail if you had to do this every single time? Well, let's compare. All right, let's go to STAT, regression, simple linear regression. We'll let X predict the observed Y. We'll get into all this in a future video. And really, that's about all I want to do here for this illustration. Compute. And guys, right down here you'll see analysis of variance, which is a ANOVA table. Do the degrees of freedom 1, 1, 2. Now they put the degrees of freedom first. That's fine for the model and the error. Sum of squares was 77.357. The error was 8.64. Our total sum of squares was 86. You can see that our mean square is just the sum of squares divided by the degrees of freedom. You can see our F statistic is 8.95 as we calculated by hand, and you can see our p-value is 0.205. Guys, we've got a lot left to learn, but that's that's kind of a critical part. Now, guys, what's this tell us? The ANOVA table tells us if our set of predictors, now set of predictors, you might come over here and say, Dr. Darbo, you only got one predictor. Guys, again, we're setting a procedure that is ultimately leading us to multiple regression, where we will have a set of predictors. But right now, our set of predictors kind of redundant. We just have one of them. So anyway, our ANOVA model in general tells us if our set of predictors predicts Y significantly. Well, guys, our p-value was equal to 0.205, which is greater than or equal to the standard setting of 0.05. So no, our model is not a significant predictor of our Y value. Now guys, I don't want to get too technical here, but what I chose a really small data set, only 3 measurements. And I did so it would be manageable in my calculations. What ends up here is we don't have enough power to actually to create a p-value. So if our model is statistically significant, we don't have enough power to detect that it is. Guys, I think I'm going to end here. More stuff to come. Take care.